here or here. You gotta kind of look harder at nature, go back and do theory. Now look, what I'm excluding here is, can people do experiments wrong? Yes. Can there be all types of statistical errors and things like that? So there's a whole bunch of, little caveats that we can put with the experimental thing. But assuming that the experiment was done right and everything, if your experiment doesn't equal your theory, then no matter how smart you are, no matter how many Nobel Prizes you've won, your theory is no good. Right? And then the other thing is that in physics, it's kind of we're in a funky place. If your theory equals your test, all right, it's kind of a bummer, because what have you learned? Like nothing, all right? So I have this great theory and it works, right? I'm not smarter at the end of the day, all right? And so what happens in physics is we spend a lot of time trying to find a better test, a new experiment that tries to break our theory. Because then once we finally do break our theory, we got to go back and we've got to make our original theory better. All right? And so that's what I've been doing. I do a lot of fundamental physics. I mean, that's what my interest is. That's the work I'm doing at Yale and the stuff I did at CERN. It's kind of taking the best that we know today and trying to break it. All right? So that we can get smarter. All right, but here's a couple things. What I also want to stress about this is, one, a consistency with the past. Because when I'm looking at nature and formulating a theory, am I looking at one event or am I looking at the entire history of knowledge? I mean, I kind of set it up. I'm looking at everything. So like I can't out of a blue just try to solve one event and come up with a theory for that one event and get all excited because I've got that one event right. I've got to come up with a theory that's essentially consistent with everything else I knew.
As Feynman said, it's creativity in a straitjacket.
It's creativity, yeah. So, damn, you have to mention Feynman. So I've stolen almost everything from Feynman. All right, I'll fess up to it right now. All right, you guys probably all know Jeremy's on to me. All right. But this is all Feynman stuff. All right, just not as good. All right, but it really is. It's creativity with a straitjacket. All right. I'll put it in a different way. All right. So how many of you guys are outside the box thinkers?
I know it.
Okay. So when you're an outside the box thinker, right? What's the next step?
Trying to find out what box you're actually in.
Okay, yeah. So you ask a question, right? So if you're an outside the box thinker, well, my kids when they were 2 were great outside the box thinkers too. You know, the moon's made out of cheese. That's great outside the box thought. Are you done?
Right.
The moon's made out of cheese? No. What do you want? You want to find out if it's right or not. So outside the box is really crap. It's for people that either one, don't want to actually know whether their ideas are right or wrong, or they're really just doing the scientific method and they're too good to call it the scientific method. All right?
Right, and then there's the interesting parallel though, is that there's in physics that's the case, but in society there's the whole, outside the box and outside of a certain standard programming, it's a whole other topic. So when you're having a social discussion and you're providing observational data, Noam Chomsky's an outside the box thinker. When it comes to the social things.
Okay, so what is he trying to get? Well, we can talk about later about it. He's an outside the box thinker, but he's trying to get things right.
But he does get things right.
So what is he doing?
Right.
Okay,
but you're saying the same phrase, it just means different things.
Noam Chomsky, in my opinion, is doing this.
He is doing that.
But I would never call outside the box thinker.
He uses observation, but outside
I know a lot of people do.
Outside the box that society is typically in, based upon your being.
Look, I deal with outside the box thinkers all the time. They come up with a new solution to gravity, a new solution to quantum mechanics.
I know what you're saying.
And I say, show me something. That's not the point. I'm free. I can do this. I can do that. Well, my little kids can come up with it.
Right.
So the important thing is to get stuff right.
Right. And this is like.
And no one is trying to get things right.
Right. And that phrase is just something you can take in different ways. All I'm saying.
So here's the point, is that we now live in a society where that's not the case. Because people go outside of the box and they'll come up with a theory for example, UFOs.
I'm not saying
Right.
that. I'm saying like people.
And so when I argue about UFOs, then what they say is I'm not an outside of the box thinker. And I'll say, I know I'm not outside the box because I want to know if they're real.
Right.
Okay, but we'll get into discussion later. All right, so this is the scientific method. So one, we want consistency with the past. All right, but we want another important thing that is very important that people leave out in theories. And what is that? There's one last thing. And I guess it's related to this, but. What's that? What? Error? Well, okay. All right, hold on. It's predictive ability. So it's just not good enough to get everything that you used to know right. A theory has to go beyond that and give you predictive ability. Okay, and so here's the problem. For example, I won't get too far into this, but I'll just say why intelligent design is not a science, right? Because intelligent design has been trying to be thrown as a theory, but it has no predictive ability, all right? So because it has no predictive ability, you can't test it, you can't really do anything. You can just let things happen, and then after the fact kind of fit the story to things that happen.
I like your example with the dots on the line and
Yeah.
the graph and.
Yeah, so Jeremy remembers this, and it goes like this, all right? Thank you, Jeremy, I would have forgot that. So, here's some data. Here are three data points, right? All right, so there's of course error bars here. Okay? So a student, and this was done by a friend of mine who did his PhD with me, his name's Tim Grove, and he's in Indiana. And so he and I talk about these things a lot. All right, so Tim Grove is great. All right, so one student A goes like this, and says, from the data I have y equals mx plus 2. All right, and then another student comes up with this. Oh crap, I gotta do it higher, sorry. Another student comes up with this theory. Alright, so this student is on y equals a sine omega x. Who's right?
Take.
Okay, either one right now. Alright? The point is, and Jeremy, thank you for reminding me of this, because it's huge, dude, alright? Appreciate it. Alright? The point is, it's no good to just get the past right. Both of these theories get the past right. Alright? So let's go and do another experiment. You get another data point. And let's get the data point right there. Okay, and the data point comes up right there. Okay, so it looks like the first student is more right, correct? Yes. But look what the second student goes, he goes, oh no, wait a minute. I just made a mistake. Alright, what I really want to say is y equals a sine of n omega x, where n is some whole number. Alright, and when you do that, it just does this. It makes more things right here. Alright? So now it looks like both are right again. Right? But then you say, okay, well, what about out here? Let's do the point. Alright, so I kind of made it, but let's do this point. Alright? We'll do that point. What did this person have to do? I meant to do it on the line, right? So this point is still fine. What did this person have to do? They had to adjust their theory. So you can see what's happening is that both theories completely adequately describe the past. But only one theory has the ability to get things right in the future, in the prediction. We live in a time where people are simply looking at the past and fitting whatever they want, whether it be politics, whether it be science. They're looking right now and they're looking at their past and they're fitting whatever theory they want. I can have any theory I want and work backwards and make it work with the past. Even politically, I'll say. I can make it work in the past, but there's only one that gets the things right in the future. And I'll kind of give a case in point. Last year, we had a student that did this course, like in art history or something like that. And he had a theory. He goes, watch this. He goes, I came up with a completely bogus idea. All right? It was bogus and it was wrong. All right? But what I did is I went to the library and the web. And there's so much information in the library, there's so much information on the web. I was able to pull out enough references to fit my theory to the past. So he was able to go back and find enough references and enough stuff on the web, all right, to fit his bogus theory. And he passed it into the professor, and the professor did a great job. All right? And so that professor completely misunderstands the idea about how to be a good, critical, solid thinker. Anybody can fit anything they want, any theory you want, to stuff that happened in the past. In mathematical words, it goes like this, that there's enough out there to form a complete basis set so you can fit anything you want. But that complete base set might not be legitimate. It may not be the real thing that's going on. All right? I know that's deep stuff, all right? And it's an interesting perspective on thinking, and critical thinking, and decision making. And it's based on very mathematical principles that most people cannot comprehend. All right? But it's important. All right, so this is the whole idea. You know, so Michael, he says 100% right, but you know, if you try to write that on a sheet of paper, you end up going for days. I'd rather just draw a picture and algorithm. Right? So you're going to be consistent with the past and predict the future, and that's how you become a good scientist. And I guess the last point about this is, when is this done?
Science all the time.
What's that? It's never done, right? So is science ever done? Is a theory ever complete?
Oh, no.
No. So is there really such thing as laws?
There's high probability of that.
Yeah, there's no such thing as laws. And so here's what happens. Here's how to abuse this. Because science never ends. Let's take evolution, for example. All right? Evolution is completely consistent with 95% of the past. And we have a theory, evolution, and it predicts things. It predicts mutations and changes to fit the environment over time. And you go and do those experiments with flies and it works. All right? But it might not work on like 5% of things. There might be 5% of things out there that are done. Does that 5% mean this theory is wrong?
No, it's incomplete.
It's incomplete. All right? So that 5%, you can't toss it out because of the 5%. It just means that we have yet to understand the theory well enough, perhaps. I mean, it might be wrong ultimately, in which case we'd abandon it. But it's got 95%, so we go and we see how it can be fixed, how the theory can be fixed. Yeah.
Well, like, who's to say that there's like definitely one theory like that could encompass everything?
Right, so that's why you got to do this. I'm not saying there is, but good science has predictive ability. So, so just because there's 5% that's not quite working, if you throw out another theory, what you've got to ask of another theory is, give me some predictive ability. And with that other theory, if you don't have any predictive ability, it's over here. It's a wash. It's no good. All right. Way too much stuff.
Just like of the sciences, physics is the most mature of the sciences in that it demands the most rigor.
I won't go there, but I'll agree. All right, so now let's get into Griffiths, okay? All right, so for homeworks in Griffiths is you got to read that article, all right? And what you've got to also do is read all of chapter 1.